Yes. Uh, I want to specifically talk about steels. I mean, if we are using combustion as a background technology, we're looking at areas associated with the steam generation, furnaces. We're also looking at air heating, for example. There are different applications of combustion. But in each of these cases, if we look at it, the fuel can be different. You can generate steam using natural gas, like PG, but you can also generate steam using solid fuels like biomass. So if we talk about combustion as a general phenomena with respect to different kinds of fuel, what are the differences that you observe? Specifically in the context of the control part that you mentioned, control of combustion, the optimization of combustion, and also the safety aspect of combustion.
So I think we will start with the most difficult of them, solid fuels. So I'll talk a bit about the biomass. So if you look at solid fuel, so we spoke about the combustion triangle earlier during our talk. It is important that for the combustion to go on, we have fuel,
Yes.
we have oxygen, and we have an activation energy or high temperature or a flame.
Right.
Now, unless all three of them are available, the combustion process doesn't start and it doesn't go up.
Right.
One of them is going to be a limiting factor which is actually going to stop combustion. In fact, in this I would want to relay a small example. I've heard of instances where fire within apartments had been basically put off by letting a small limited explosion go.
Right.
Now, how does it help? The small explosion actually takes off the oxygen around the flame.
Right.
So what it does is the flame extinguishes.
Right.
So we've had similar instances even in larger cases where for the explosive squads, they take off the oxygen which is available
Right.
by a controlled explosion. So they limit the larger explosion.
Right.
So what we're trying to do here is, when it comes to solid fuel, so in solid fuels, the fuel will always burn on the surface. Because it is only on the surface that you have oxygen and you have the activation energy, the high temperature, the flame which is available. So as the fuel will keep on burning on the surface, the old surface will give away, it will flake off, and it will expose the newer surface.
Yeah.
But at the same time, there is going to be a lot of solid fuel. By definition, if you represent biomass or for that matter tool, the basic constituents, if you do a proximate analysis and ultimate analysis, it will have a lot of volatile matter and it will have a lot of moisture.
Correct.
So solid fuel, when basically it burns in a grate, biomass because essentially they are burned either in fixed beds, in manual fired boilers. So or they are actually burned with a still so in moving beds. So now in those, when the fuel starts getting experienced with a higher temperature, the moisture starts getting released.
Right.
The fuel as such, you don't have moist fuel which is actually burning. The moisture has to be relieved.
It needs to go away.
It needs to go away first. So that actually takes away a bit of the energy which is produced as a result of energy.
It's the HMG of
Something
moisture.
that, we spoke about this. So during the monsoon, when you have moist biomass and all, you have a problem. You have not less energy which is available. So first, this moisture disappears. This actually opens a lot of pores. So the moisture which is ingrained starts coming up through capillary action.
Right.
And even that starts evaporating. So what you have in the second zone is a much more drier mass.
Yeah.
And then you have a lot of volatile products. So volatile organic matter which is there in the solid fuel. Now the higher the volatile matter, the better it is. As far as the calorific value is concerned, and the burning is concerned. So this volatile matter then boils. It is only then that you come down to the fixed curve. That is why you see, if you look at various zones, so the first zone there's hardly anything. The second zone you have a large flame because most of the volatile matter which is actually burning. And
The volatile matter actually burns in a flame. Okay, so any biomass, the
Yeah.
flame that you see is the volatile matter.
yes, so what you see, the flame, is actually the volatile. Then subsequently, when it comes to the fixed carbon, you have those embers.
Right, right.
So they take a longer time, because then that is the area where you have the layering.
Right, correct.
Where we come in over there is we have zoned.
Yeah, right.
So we have a zone where you basically dry the fuel.
That,
You have a zone where volatile matter basically burns. So the area in the furnace is designed in that fashion. And then subsequently, as the fuel moves on, it then comes on to the area where the fixed carbon blows. Then that requires a certain amount of air, certain more amount of air required, because that is a much more slower process. So we are able to basically sequence all of this and burn it in such a fashion that in the end we are left with holy ash.
right.
So we don't end up a situation where your ash has a lot of unburnt in it, because that is a loss.
Second.
Because that is something that you paid for, and we don't want a situation where the customer basically feels that this is a calorific value which could have been utilized, but now is getting ended up in the ashes.
Yeah.
So in terms of control, very important, because if in the case of solid fuel, if we are not able to blanket the solid fuel with air in the correct fashion, then we will have a problem, because we will have a lot of unburns. We will have carbon monoxide. And these unburns can potentially cause a problem.
Right.
So those are things which we may want to avoid, and at the same time, we don't want to an unlimited supply of air.
Right. Because that is a
Still
very
want
loss.
the process to be efficiently done.
Yeah.